Hello, I hope all of you are doing okay. Now this video is for AQA 2022 exams and we're thinking about the first physics paper you're going to be doing, and that's if you are doing Trilogy and you're doing foundation level. So that means this video is going to be perfect for you. If there's anything that you're not sure about, you can find full videos over at GCSEPhysicsOnline.com about every single topic. But in this video in particular, I'm going to use the information from the advanced information. I'm going to be going through energy changes in a system, the national and global energy resources, current potential difference and resistance, changes of state, and finally atoms and nuclear radiation. I'm also going to be going through the two required practical activities you need to know about, number 14 and number 16. A few topics will not come up in your exam this summer. They are domestic uses and safety, the particle model and pressure, and atoms and isotopes. So they won't be assessed in this paper, but other parts of the course could be assessed in paper 1. The other thing, if you go to my GCSE website, which is GCSEPhysicsOnline.com, you can download a completely free copy of my AQA revision book. It's going to be useful for foundation students as well. And this has learning checklists and some extra tips about how to revise for your coming exams. So let's get started. Now, energy is a bit like money, and it can be stored in different places or maybe transferred from one store to the other. And we can also think of it a bit like a liquid that's maybe transferred from different store to different store. Now there are a number of different stores that we need to consider. So we have kinetic energy, which is due to how quickly things are moving. We've got elastic potential if you maybe deform an object, like you squash it or squeeze it. Gravitational potential is to do with how high you move something. And then we've got thermal, which is the internal energy store, as well as a few others. Now what we can do is, with energy, we can actually work things out. And if we wanted to work out the kinetic energy, for example, the kinetic energy is equal to a half mv squared, where the v here stands for the speed of the object, and that's measured in meters per second. We should always measure our mass in kilograms, and then this means that the unit for energy is the joule. This energy is equal to a half ke squared, where E is the extension of that object, not how long it is completely, but how much longer it has become. And again, what we do, we measure our extension in meters. K is the spring stiffness, and this is measured in newtons per meter. And once again, we measure our energy in joules. Our gravitational potential energy, EP, is equal to mgh. So here again, we have our energy in joules, our mass in kilograms. H is the height that something's moved through in meters, and G is what we call the gravitational field strength. And on Earth, this has a value of 9.8 newtons per kilogram, but this does depend on where you are in the universe. Some things like the moon, for example, have a much smaller value of their gravitational field strength. When it comes to looking at thermal energy, what we can do is we can change the thermal energy of something by looking at mc delta theta. So here what we have is our theta, that's our temperature, and that's measured in degrees Celsius. We measure our mass in kilograms, and this thing down here, little c, is our specific heat capacity. And this is the amount of energy required to raise the temperature of 1 kilogram of something, of the substance, by 1 degree Celsius. So that means the unit for this are joules per kilogram per degree Celsius. So we have these different stores of energy, but what we can now consider is the different ways that energy is transferred from one store to the other. And there are 4 main transfers that we need to think about. So these are our 4 transfer processes. You've got heating, electrical working, radiation, and this could be things like sound waves, or it could be light waves, and also the rest of the parts of the electromagnetic spectrum. And finally, we have mechanical. Now, it's really important to look at the way that energy is transferred from one store to the other. And what we might consider is at the start of a process, we can maybe consider the energy store. We then need to define a clear end point, and we can consider how the energy is stored at this point. And what we can then do is think about the transfer as well. So these are some of the things we need to think about. If you've got an object projected upwards, maybe it starts as the kinetic energy store and ends up transferred to the gravitational potential store. If you've got a moving object hitting an obstacle, it might end up going from the kinetic store radiated by sound perhaps into the thermal store of the surroundings. If you've got something which is accelerating, depending on what provides this force, you might then increase the kinetic energy store. You've got to be familiar with all of these and get used to doing different problems where you might have different energy stores, and that just comes with practice. It's also worth considering how quickly that transfer takes place, and what we can then think about is the idea of power. So power is defined as the rate at which energy is transferred or at which work is done. Now we can say that power is equal to the energy transferred divided by time, and the word rate just means the amount per second. Or we can also look at power as the work done per unit time. And we always measure energy and work done in joules. If we measure time in seconds, this then gives us a power measured in the watt. And finally, we can think about energy resources. And what we're talking here is about things that are maybe used for transport, for example, cars. We might think about electrical or electricity generation. And finally, we can also use these for heating our homes and businesses. What we then need to do is think about maybe different ways in which we can generate electricity. There are two main categories. We've got non-renewable and renewable. Non-renewable resources, once they're used up, we can't replenish them. So we're thinking about coal, oil and gas, as well as nuclear fuels. And when we talk about nuclear fuel, we're often thinking about uranium or plutonium. When it comes to renewable energy resources, so we have biofuel which can be burnt, and the reason that we burn all of these or use this to generate heat is to boil water. Water turns a turbine which then turns a generator which generates electricity. One way we can get away with not burning things is to use wind turbines, where it's the power of the wind directly which is causing the generator in the top of this to turn. We can use solar cells which turn that sunlight into electricity. We also have geothermal, hydro, wave and tidal, where these are just different ways of having moving water hitting a turbine blade to cause a generator to turn. So this video is a summary of the AQA electricity topic. And what we have in electrical circuits are a load of small electrical components. And what we need to do is we need to draw out circuits, and to help us with this, we have some circuit symbols. So some of these might be common from before, but there's a few extra ones, things like light-dependent resistors, diodes, and so on, that it's worth just spending the time memorising what all of these stand for. And the reason for this is it allows us to draw circuits really simply. Now, in the simplest case, we might have a power supply, so a cell. We might have an ammeter, and you always put the ammeter in series, and this is connected to maybe a lamp. And when the circuit is connected, it starts shining. We can also use a voltmeter to measure the potential difference across a component. So it's always worth remembering that ammeters go in series and voltmeters go in parallel. So what we have here is our really, really simple circuit. Now for this one here, what we can think about is the rate of flow of charged particles around the circuit. That's what is transferring the energy from the cell, in this case, to the lamp. And we've got to remember that electric current is the rate of flow of electric charge. Now, one of the equations we can use is that Q is equal to I times T. Now, somewhat confusingly, we use Q as a symbol for charge, and charge is measured in coulombs. We use I for the current. This is like the intensity of current, and we measure the current in the unit of the amp, and then time we measure in seconds. And really what electric current is the flow of electric charge, and in a circuit like this where we have maybe a DC supply, so it's a direct current, we've got the flow of electrons in the wires. Now we can also think of this electric current which is going through a component. It depends upon the potential difference across it, V, and also the resistance of that component. Effectively, we're going to have a bigger current flowing if you've got a bigger potential difference, but if you have a bigger resistance, that reduces the current. And what we have here is V stands for our potential difference, and this is measured in volts. R is the resistance measured in ohms, and then once again the current is measured in amps. Sometimes a more useful equation is V equals I times R, and you can apply this to any part of the circuit. If you know the potential difference and the resistance, you can then work out the current that is flowing. But when it comes to resistance, we need to look at the resistance of certain components. And we can set up a simple circuit a bit like this, and what we have is a power supply. we have a variable resistor, and this then allows us to change the current and the potential difference across a component. And we can do this for the following things. And we need to look at the characteristics of resistors, lamps, and diodes. Now, if we have a resistor, what we find is when we plot values of current and potential difference, we get a straight line that goes through the origin. And what this means is that as you have a greater potential difference, you've got a greater current that flows, and that's because the resistance is constant. In actual fact, this is a great example of something called an ohmic conductor. And provided this stays at the same temperature, the current is going to be proportional to the potential difference. If, however, you have a filament lamp, this isn't an ohmic conductor, and what we find is we get a graph that looks a bit like this. What that means is, as this gets hotter and hotter and gives out more light, the resistance increases. So this one here, you've got a changing resistance for this light bulb. If you have a diode, on the other hand, the whole point in a diode is it works a bit like a one-way valve, and it only lets the current flow in one direction, so we get a graph like this. Effectively, if you've got a negative potential difference, the value of current is 0, but when you have a high potential difference, loads of current can flow through, and this really allows us to control the way that current flows in a circuit. Now, there are two other components that we can investigate. One of them is a light-dependent resistor, and if we look at the resistance and the amount of light intensity, with an LDR, when we increase the light intensity, the resistance decreases. And the same kind of thing happens when we have a thermistor. So a thermistor is a thermal resistor. Once again, if we have the resistance on this axis of the graph and we look at the temperature on this axis, as we heat this up, the resistance goes down. And these two components can be used for all sorts of applications where maybe these can be used to sense something. So if it gets too hot or gets too dark, we can use this to turn on other parts of an electrical circuit. So this video is revision of the particle model, which is something that we use in physics to explain the world around us. Now, the first thing we're going to consider is something called density. Now, density is basically a measure of how much stuff there is in a given volume. So perhaps we have two things which have the same volume. So I'm just going to take this off. What we have is the same volume of material here, but this one here is a lot heavier. It's got a bigger mass, and that means that there's effectively more stuff in the same space. Now, the way that we work out density, we use the symbol rho, so RHO. This is a Greek letter that we use to represent density, and it's equal to the mass divided by the volume. Now, because we always measure mass in kilograms and we tend to measure volume in cubic meters, this then gives our density in kilograms per cubic meter. Although sometimes if we were to measure our mass in grams or volume in cubic centimetres, we could also, depending what we're measuring our quantities in, we could maybe look at the grams per cubic centimetre. Now, this particle model allows us to look at solids, liquids and gases. And if we think about the behaviour of the individual particles or molecules, this explains why certain things have certain properties. So I'm just going to consider solids, liquids and gases. So in a solid, we have this close, packed, regular arrangement of particles. Now they're still jiggling around, they're still vibrating, but they're not really able to move around that material. So that's why a solid is what it is. A liquid, on the other hand, the particles are still really densely packed together, probably a similar density to in a solid, but here they're able to move past each other. And what we have is this random motion of all the particles in a liquid. In a gas, on the other hand, the particles are really spread quite a long way away. They're moving quickly in all random directions, and because of this, we can do things like we can compress a gas or whatever. So let's think about how we go from one state to another. Now, if you have a solid and you heat it up, it turns into a liquid, so that's when it's melting. The liquid then might boil and turn into a gas, but if we have something which is evaporating, this is where something turns from a liquid to a gas below its boiling temperature. This is the reason that things like puddles do dry up. Even though it never gets to above 100 degrees, that water still turns into the water vapour. Going the other way, we have gas that condenses to a liquid, and then the liquid freezes to a solid. But what we also have sometimes is a solid that turns directly into a gas. You might have seen this with some carbon dioxide pellets, and this is what we call subliming. And the key thing to remember is when we move from one state to another, there's no chemical reactions happening, it's just a physical change, which means it can be reversed and they can go back to the state they were in before. Now sometimes we have unstable isotopes, and if you have an unstable isotope, it tries to become more stable by giving out particles or something from the central nucleus of that atom. And there are a few different sorts of radiation. First of all, we have alpha radiation. This is made out of 2 protons and 2 neutrons, and that means it's relatively heavy and it's also very ionizing. It's got a charge of +2 because of these 2 protons. And when we talk about things which are being ionizing, effectively that means if they smack into another atom, they can knock off electrons and make the atom into an ion. Now that can be dangerous for people because that then changes the chemical properties and can cause mutations and cancer and so on. So first of all, alpha radiation emitted from the nucleus, very heavy, and it's got a very short range. The next type is beta. And beta radiation is a high-speed electron which is emitted from the nucleus of the atom. This has got a charge of -1 because it's an electron. And actually what's happening inside is that a neutron turns into a proton and an electron. So this is then emitted. It's quite ionizing still because it's got a charge of -1. It's got a longer range than alpha, but it's not as dangerous because it's not got such a big charge. The third type is gamma radiation. Now this one here isn't actually a particle, instead it's a burst of electromagnetic radiation. It's a wave, and that means it's got no charge. It is ionizing because this wave can still cause electrons to be taken off another atom, but it's also got a really, really long range, and it's really hard to stop gamma radiation. And occasionally, sometimes we also get neutrons which are emitted. And once again, the neutron, what it's going to do, it's just going to disappear from that nucleus, it goes flying off, and maybe some of the energy of this neutron could cause something else to become ionized. So neutrons, again, have no charge. That's a kind of sort of fairly rare kind of nuclear radiation. But what we can do is we can show these with some nuclear reactions, a bit like the way that we show chemical reactions. Now, the way that we show alpha in terms of this nuclear reaction is we maybe start with a radioactive isotope, and what happens is it gives out an alpha particle. Now we give the alpha particle, because it's the same as the helium nucleus, because it's got 2 protons and 2 neutrons, we can often represent an alpha particle as He for helium 2,4. Now what happens is that this number here, the atomic number, goes down by a factor of 2, because we've got rid of 2 protons, so it's Z-2. And the mass number goes down by 4, because it's got rid of 2 protons and 2 neutrons. So the number at the top goes down by a factor of 4. And this then makes a new isotope. If we did the same and looked at beta, again we might have an element X. You know, this is just a made up thing. And what happens if it gives out beta radiation? This is the same as an electron. And effectively an electron, we give it the number of 0 and -1. I'll talk about why that is in a second. Now this thing here might decay and it might make a different isotope Z. Now the mass number doesn't change because all that's happening inside is that a neutron turns to a proton, so it's still got the same mass in the middle. But because we now gain 1 proton when there was a neutron before, that means the number at the bottom increases by 1. And what we can see is that this number here and this number here add up to that number there. So what we're doing is we're conserving the atomic number and mass number in this reaction. So this is a way to represent beta emission. Now when it comes to looking at radiation, there are 2 things we can think about. We've got activity, which is the amount of alpha or beta particles which is given out. So that's the amount given out per second. But what we then do is we actually count this using some kind of radiation detector, often a Geiger-Müller tube. So count rate is the actual number of decays recorded each second by the detector, while activity is the total amount given out from that nucleus. And actually the thing about radioactive decay is it's something which is spontaneous and random, and there's nothing that we can do to influence. But what we can do is we can look at the decay of something over a period of time. So maybe we have the activity, or the number of nuclei up here, and here we have time. And what we find is over time we get a graph that looks like this. And the important thing is that if we look at a certain amount of time, and we look at the activity, after a certain amount of time the activity is going to decrease by half. After the same interval again, the activity decreases by a half, and again after the same interval it decreases by a half. And this time down here is what we call the half-life. And there are really two ways that we can define this. Either the time it takes for the number of nuclei of the isotope to half, or the time it takes for the count rate or activity in the sample to fall at half of its original level. So these are two definitions you need to know about. And effectively what this means is that it doesn't mean that after 2 half-lives everything is gone. It just halves and halves and halves and halves. And this line kind of never really gets to the bottom. And there are 2 further things we can think about, which are irradiation and contamination. Now, irradiation is basically you expose something to nuclear radiation, but that doesn't mean that thing then becomes radioactive. We can actually expose food to radiation to kill the nasty germs, but it doesn't make the food radioactive. However, contamination is when you actually get some of these radioactive particles mixed in with whatever the sample might be, and then that thing then continues to emit radiation and is contaminated. Now in this experiment we're going to be measuring the specific heat capacity of a metal. This one here is aluminium, and you might have seen something similar at school. Now there's an equation that says the energy supplied is equal to the mass times the specific heat capacity times the change in temperature. And in order to work out the value of C, the specific heat capacity, we need to know the mass of this piece of metal. We need to know the change in temperature and also the energy supplied. Now, the change in temperature can be measured using a thermometer, and that actually just fits in the hole in the top of the block like that. In order to supply energy, we're going to be using this immersion heater, and we do that by immersing the heater in the big hole. And so this is a fairly standard setup. But how much energy is actually transferred to it? Well, there's an equation that says energy is equal to the power multiplied by the time. So we can record the time using a stopwatch over here, and the power supplied to this, we can actually work this out from the current and the voltage or potential difference. And we can measure both of these using either an ammeter or a voltmeter. So if we know the amount of energy supplied and we know the change in temperature, we can then plot that on a graph a bit like this. And then when we get some data points, we can use these to actually work out the value of that specific heat capacity. So in this experiment over here, what I'm first going to do is I'm going to measure the mass using a mass balance. So I'm going to turn it on. This one over here, we can adjust the unit. At the moment it's in grams, which is really useful. And so if I take this block, it's about 1 kilogram, but just to confirm the mass, I'm going to zero it. So it's zeroed, and if I put this on top, the reading is 1005 grams, so 1.005 kilograms, roughly 1 kilogram but not exact. So I've got the mass of this block. What I'm then going to do is just put that to one side. I'm going to actually do this on a heat-proof mat. And this just means that as this gets warmer and warmer, it's not going to burn the table underneath. So I have my block here. In terms of the circuit, well, I've got it actually plugged into this power supply. At the moment, when I turn this on, it's a reading of about 10 volts. So we've put it up fairly high. The exact number doesn't matter. And the first part of the circuit is going to go from the power supply, and we've plugged it into DC. It's going to go through an ammeter in series, and the first thing I'm going to do is just check this is working. So if I just put it in there, I just want to see there's actually a reading on the ammeter. If I turn that on, we have a reading of 3.35. So we know the circuit's working, and then we're going to put the voltmeter in parallel across the heater. So I'm just going to plug it in like so. So this is a setup. We've got the block, the heater, it's connected up here to the power pack, but I've not turned it on just yet. And we've got my stopwatch over here. Now the other thing we're going to do is we're just going to put the thermometer in the hole, but you can actually see it's not a great fit. And that means we might not be actually registering the temperature of the block. So what I'm going to do is just put a small amount of water in this hole to basically fill up that air gap. I've added a small amount of water using a pipette, and if I just put this in, we can see that fills up the hole like that. Now you could use oil, or you could use some special kind of conducting paste, but that just gets a little bit messy, so water is going to be good enough for this. And what I'm going to do is I'm going to record the time every minute for 10 minutes, and what I'm going to do is as soon as I turn this on, I'm going to press start on the stopwatch, and then we can then record the temperature on the thermometer. And it's really important just to note that it's always good to keep your eye level at the same height as the reading you're taking on the thermometer. So hopefully you can pick that up on the camera. So we're now going to leave this for the next 10 minutes, taking readings of the temperature every minute. So we had a mass in kilograms of 1.005. The values for the voltage or potential difference and the current, they fluctuated very slightly, but I basically took these values. Now I could have chosen maybe 9.59 or 3.39, but I decided to go for these because it seemed to be these values for the longest amount of time. And to work out the power, we're going to use the equation that says the power is equal to the potential difference multiplied by the current. So in this case here, the electrical power is going to be equal to 9.58 multiplied by 3.38, which equals 32.38. So I'm just going to write down my value for the power as 32.4, and that's measured in watts. Now to look at the total energy transferred, the energy transferred is equal to the power multiplied by the time. And here we've got time in seconds. So we've got 0, 60 seconds or 1 minute, 2 minutes, 3 minutes and so on. So to get the values for the energy transferred in this column here, I'm going to multiply this number here, 32.4, by the number of seconds. So after 0 time, we had 0 energy transferred. After 60 seconds, we're going to have 32.4 multiplied by 60, which equals 1944. So I'm just going to leave it like that. So now we have some data here for the energy transferred in joules. I must say I've kept it with no decimal places. I've maybe gone to more significant figures than I can really justify. But when I come to actually plot this on the graph, I suppose this one here, for example, 11,664, I could probably plot to the nearest 100 joules. So this is the data for the energy transferred in joules. We're going to put that on the x-axis, and we're going to have the temperature on the y-axis. So on my axis, I've got the energy going from 0 up to 20,000 joules, and I've got my temperature going up from 20 degrees, where we started at, up to the final temperature of 35 degrees over here. So I can now start plotting my data. So I've now plotted the data, and if I put my ruler next to it, we can see there's definitely this trend where we can fit a straight line. But the thing is, this straight line doesn't go through this point over here. And there's actually a bit of a curved start to this graph. And the reason for that is it takes a small amount of time from when we actually plug the heater in and start it heating up the metal block for that to cause the temperature in the thermometer to start rising. There's a bit of a time delay at the beginning. So what I'm going to do on this is I'm just going to fit my line of best fit to this data over here. And I think that's appropriate. And if we were to follow this data back, we'd have a bit of a curve at the start. Now the important part here is the straight line. So what I'm going to do is work out the gradient of the straight part of this graph. I'm going to do that by drawing in a triangle onto this line of best fit, and I'm going to go from this point here to that point over there. Now, in order to work out the gradient, I'm just going to put my values in. So this one here is at 19,000 for the x coordinate, and the y coordinate is 35. Whereas this point on the line over here, the x component is 4,000 in terms of the energy, and then we've got a temperature of 22. Okay. So in order to work out the gradient is equal to the change in y value divided by the change in x value. Now the change in y value goes from 35 take away 22, and we're going to divide that by the change in x value, which was 19,000 take away 4,000. which equals 13 divided by 15,000, which equals 0.00086667. Okay, so this is a value for my gradient. Now we can use this value here for the gradient to actually work out the specific heat capacity of this aluminium. So the change in energy transferred is equal to mc delta theta. And we can rearrange this to say that the specific heat capacity is equal to the change in energy divided by m delta theta. Okay. Now this is related to the gradient because the gradient of that line was equal to the change in y value, which was our change in temperature, divided by the change in energy, delta E. Okay, and here we've got delta E over delta theta, but here we've got delta theta over delta E. And if we actually do some rearranging, we can then say that this specific heat capacity is equal to 1 divided by mass times the gradient of that line. Now if we put some numbers in, this is equal to 1 divided by the mass, which was 1.005 kilograms that we took when we actually put it on the mass balance. The gradient is this value here, 0.00086667. And so I've got my value still saved in the calculator. I'm going to multiply it by 1.005. And then I'm going to do 1 divided by this answer. And this gives me a value on the calculator of 1148.1. Okay, now really, because we could only measure the temperature to the nearest degree, and that's something which it's a bit tricky with the thermometers, is it 31, 32, and it's really your judgment about the value that you take. We should only really give our final answer to 2 significant figures as well, like our raw data. So here, we can say that the specific heat capacity of aluminium is about 1100. And the units, because we're looking at joules per kilogram per degree, are joules/kilogram per degree Celsius. So this was my final answer for the specific heat capacity of aluminium, which is actually bigger than the value that we tend to normally find. Normally the value for aluminium is about 900 joules per kilogram per degree Celsius. So we actually had a higher value. So this aluminium block wasn't insulated, and that's the reason why we actually had a higher value than the kind of true value that we should have been approaching. So basically, as we were supplying energy to this, we weren't just heating up the block of metal, we were also heating up the room that it was in as well. So we could actually get a lower value and a more accurate value if we were to insulate the block, if we were to do this practical again. So maybe have a piece of polystyrene underneath it to reduce heat loss from the bottom, maybe some bubble wrap or some other kind of insulated material wrapped around the sides and on top of it, and that would actually give us a better value for the specific heat capacity of this metal. But there we go. I thought that this experiment here, there's quite a lot of analysis that you have to do. You've got to not only plot your data, you've actually got to put a straight line of best fit that doesn't necessarily go to the origin of this graph over here. You've then got to work out your gradient. You've got to use your value for the gradient into this equation over here, and this will get you a value for the specific heat capacity. But there's quite a lot of advanced maths that you've actually got to understand to do this practical. So that one there was how we work out the specific heat capacity of a solid object like this metal. Now in this experiment we're going to be looking at the IV characteristics of a resistor. So this is my resistor here, and I'm just going to put it into this component holder to hold it nice and firmly. I then have an ammeter which we're going to be using to measure the current, the I, and we've got a voltmeter to measure the potential difference, the V. So what we're going to be doing is plugging this into a circuit. We're going to change the current and the potential difference through it and across it, and then we can take some data. So you can do this with a battery and a variable resistor. For this one though, I have a power supply, and what we can do is we can vary this. So this allows us to change these values. Now the first thing that I'm going to do is just check that we have some readings, and if I just connect this into the DC output, I'm just going to make a very simple circuit with the ammeter, and this just means I know that we have all of the components working as they should. So if I put those in there, plug this in here, as I now adjust the value here, we can see that we have a current inside that component. Perfect. So I'm going to put that back down to 0. Then I'm just going to connect up my voltmeter. The colour of the leads doesn't matter, but this just allows me to tell which is the ammeter and which is the voltmeter. And then this voltmeter is going to be going in parallel with the resistor. And this allows us to work out or measure the potential difference across it. So again, now I've got all of these turned on. We can now see readings for the current and the potential difference. And there we go, that's all good. So I'm just going to turn that back down to 0. Now when it comes to taking data, I'm going to go from values of 10 volts, 8, 6, 4, 2 and 0. And then I'm going to turn these around so we can have some negative values as well. Now I'm not going to get it at exactly 10 volts, and I suppose this is the value that we're going to be recording, but I'm going to adjust this until this value is about 10. Okay, we can then take a value for the current, and I'm going to switch it off between readings, and that stops this component getting too hot. So I think we're ready to start taking some data. So this is the data that I took when we had this single resistor, and we looked at both the potential difference or the voltage across it and the current through it. Now I got my values by pausing the video and choosing the value at that time, but obviously some of them did fluctuate very slightly. Now when it comes to putting this onto a graph, we're going to have voltage on the x-axis and current on the y-axis. So here's my graph where we have current in amps and voltage in volts. And this one here, we can add both positive and negative values onto the same graph. So what we're going to do is we're going to just plot all of this data. So when it's 10.08, to be honest, that's pretty much exactly 10 when it comes to this graph here. And that's a value of 0.10. So that's over here. When it's 8, we've got a value of 0.08 and so on. And it goes through the origin in the middle, and then when it's -2, it's minus 0.02, and then finally over here. Now, if we can actually see pretty clearly there's a good trend, and if I use my ruler to draw in a line of best fit, we can see that this is a really beautiful straight line of best fit that goes through the origin. Okay, so there we go. And this is what we call the IV characteristic for a resistor. And what this shows is that the current is directly proportional to the voltage. And that means that this obeys Ohm's law. So if you were to double the potential difference, we'd also double the current through it. And the reason for that is that this resistor has a fixed resistance. This one is actually 100 ohms, and it's always going to be 100 ohms. It doesn't matter if we've got 8 volts or -6 volts, this will always have the same resistance. Now I suppose one criticism of these results is that the current, we only really went up to 0.10. So maybe I didn't have the most suitable ammeter. Maybe it would have been better if we could have measured this value to more than just 2 decimal places. But I still think this shows we have this good relationship between the current and potential difference for a fixed resistor. It's a straight line that goes through the origin. So we're going to be looking at the IV characteristics of a lamp or a filament bulb that we have over here. So with the power supply turned off, we've got 0 volts and 0 current. So that's one of the bits of data we need. I'm going to turn this on and adjust it to about 2 volts. There we go. And what I'm going to be doing is turning off the power supply in between readings, and that stops this getting too hot. Okay, so that's the data plotted. Again, we can see that maybe if we put our ruler here, we can't really draw a straight line of best fit. So that means we're going to have a curved line of best fit. And it's going to be kind of going here and around here. So if I just draw that like so. And again, this is why I've used a pencil in case I make any mistakes. So that's one side. I'm going to flip the paper around to do something similar with this data over here. Okay, so that is my line of best fit for a filament lamp. And what we can see is that we don't have a straight line, and that means we don't have a constant resistance. In actual fact, when we've got a higher voltage, we've got a greater current, and that means there's a greater heating effect, which actually increases its resistance as we have higher values over here. And the other thing that you might notice already from the data here is that the positive and negative values are the same, just these ones are negative. And that means it doesn't matter which way the current is going through this, it's going to behave in exactly the same way if it's either positive or negative. So this S-shape curved here is the kind of thing that you'd expect to see for a filament lamp. In this experiment, we're going to be looking at the IV characteristics of a diode, which is this very small component up here, which I've just got mounted in this component holder. Now, when it's set up, it's going to be connected in series with another resistor, and this just means it limits the total current which is actually going to be flowing through this, and that stops it overheating. Now, I've actually chosen to use these values because in terms of the data, this is where it gets interesting. All of this stuff here is just 0. And to make sure that we can actually see what happens, I've chosen values for the voltage going from 0 to 1 over here. And obviously we can have negative values if needed. So basically, let's start at 0. When you have 0 voltage, we have 0 current. When we've got negative values of voltage over here, we'd also have 0 current as well. So effectively the line is going to be going along this part of the graph. When we get to a value of 0.57 volts, so that's going to be over here, so that's 0.5, this is 0.57 here. We also have a value of 0. When we go to 7.5, which is here, we've got a value of 0.04, and then it starts to rise rapidly. And this final point here was when it actually overheated. So what I'm going to do is put in my line of best fit. It's going to be a curved line of best fit, and basically it's going to be 0 all the way back over here. So this is now the IV characteristic for a diode. Basically we have this steep rise over here, and we can see how that is different to maybe if you have a resistor where we've got this straight line, or even a lamp which has this S-shaped curve. This one here is a characteristic shape of a diode.